Imagine our universe as an incredible superhighway. Billions and billions of particles undertake epic journeys, making their way through space and time. Of these, one particle proves to be the most determined traveler, the neutrino. It's a particle that knows no borders, zipping through dense stars, enormous galaxies, and other interstellar obstacles. Think of the stories it could tell us, if only we could catch it. But how do you stop a particle that's virtually unstoppable? That's a question of science. It all began with a mathematical theory. The year was 1930, when noted physicist Wolfgang Pauli first suggested what he called a desperate remedy to a puzzling problem. Experiments had found that when an unstable atomic nucleus released an electron, the new energy and momentum didn't match expectations. In order to balance the equation and maintain the law of conservation of energy, Pauli proposed a theoretical particle. This particle had neither negative nor positive charge, and in 1933 was given the name neutrino by noted physicist Enrico Fermi. The neutrino successfully reconciled Pauli's dilemma, but it continued to disturb him. He admitted, "I have done a terrible thing. I have postulated a particle that cannot be detected." But Pauli needn't have been so distressed. It would take a few more decades. But in 1956, Fred Reines and Claude Cohen would finally announce the neutrino's detection. Its difficult detection established its reputation. The neutrino was one of the most elusive particles in the standard model of particle physics. In today's physics, the standard model gives the simplest answer to the question, what is everything made of? It provides 12 basic blocks of matter that make up the entire universe. These blocks interact through 4 forces to create all of matter. You may recognize some of the more famous fundamental particles, like electrons and photons. But lesser-known particles like the neutrino are equally fascinating.
Neutrinos is the odd man out among the fundamental particles. Neutrinos has a peculiar property. It's very shy.
What makes the neutrino so shy? It's because forces like gravity and electromagnetism, which affect you and I so strongly, have no effect on the chargeless and nearly massless neutrino. It neither interacts like electrons or protons to form atoms of matter, nor is it attracted to other heavy bodies. All neutrinos show are weak interactions, so weak that they can't be blocked or captured easily.
Neutrinos, by virtue of not having these electromagnetic interactions, you can kind of say, yes, these are clean, they are, all contamination of electromagnetic interactions is removed, and what you can study are other interactions which are weaker than electromagnetic interactions.
It's these weak interactions that give scientists the strongest desire to study neutrinos. Having virtually no obstacles in their path, neutrinos travel, most literally, across space and time to reach us. Primordial neutrinos that were born after the Big Bang still roam our present-day universe. And neutrinos generated by nuclear fusion in the solar core wash all over us here on Earth. In fact, hold up your thumbnail. Now imagine nearly 65 billion neutrinos penetrating it every second. Could it be that some of these neutrinos are coming from the Sun? Could it be that some others are nearly as old as the beginning of the universe itself? How can we better understand these exotic cosmic wanderers? Many scientists across the world have chased the elusive neutrino over the last century. India has a distinguished history in this quest, going way back to the 1960s. Within the caverns of the Kolar gold fields in Karnataka.
Indians are pioneers in neutrino research. the first ever cosmic ray produced neutrinos was detected at Kolar Gold Field in a neutrino detector 2.3 km underground in 1965. And today, atmospheric neutrinos is a rich field of research by its own right.
In the 1990s, India's neutrino program hit a roadblock with the shutdown of the Kolar Gold Fields. With the demise of this neutrino program, other countries like USA and Japan forged ahead, making new and path-breaking discoveries. It seemed as if the Indian quest for neutrinos had reached a dead end.
Unfortunately, we did not continue this. If we had continued, we would have been on the top of the world. Now, can we recover this lost initiative? We should, right? We can and we must.
This was done in 2000, in January 2000. In this institute, in IMSC, there was a workshop in high energy physics. And during this workshop, many people came together and we said, let's get together and write up what kind of physics we can actually achieve by putting up a neutrino lab in India. And that was actually the first document that we wrote up.
This is the site for one of India's most ambitious mega science projects, the India-based Neutrino Observatory, or INO, at Theni in Tamil Nadu's Bodhi Hills. What makes this site ideal for tracking neutrinos?
We need at least kilometer depth for our physics requirement. Then we need the rock quality to be good for safety. We need the environmental impact to be the least because we are going to be near forests. And so this whole combination of requirements was listed in trying to find a suitable site for INO.
Today, it's an empty landscape, but within the next 5 years, this will be home to a path-breaking experiment in neutrino physics. The INO brings together the largest collaboration in Indian science so far. This includes 26 leading science institutions and over 100 scientists who are partnering with some of India's top industries. The collaboration is led by the Tata Institute of Fundamental Research, or TIFR, at Mumbai. The INO project will dig a 2-kilometer tunnel leading directly below a 1,300-tall rock mountain to build a unique underground laboratory.
We are standing on INO land. This is about 26.5 hectares. Here, where we are standing, is where the surface facilities will come. The tunnel itself will start from the cement slab there, that is the marker for the beginning of the tunnel. And the tunnel from there will proceed like this, and you can see this white marker here is the next marker after that, and like that you have the markers all along, and the tunnel will go underneath this mountain and stop below the peak. The peak there, and underneath that it will stop, and that is about 2 kilometers of tunnel. And right below the peak you have the laboratories at the end of this 2-kilometer tunnel.
As cosmic rays pass through the sheer rock, most unwanted particles will get filtered out. The neutrinos will pass through effortlessly and enter the INO cavern. The biggest of the INO's 3 caverns will house the largest neutrino detector in the world, the iron calorimeter, or the iCal. When completed, the iCal will be a massive sandwich of magnetized iron and detector plates. Here's how it'll work. Chargeless neutrinos will pass through an immense magnetic field and transform into charged particles known as muons. Depending on the muon charge, they will bend inside the powerful magnetic field. The charged muons will now trace a curved pathway of electrical signals. 30,000 highly sensitive detectors called resistive plate chambers, or RPCs, arranged in 150 layers will pick up the signals. 3.6 million electronics channels will carry the data to computer systems. This is the heart of the experiment that will study the properties of the neutrinos, continuing the arduous scientific quest that Wolfgang Pauli began in 1930. It has never been easy or quick to crack the secrets of the neutrino. In the 1930s, Pauli and others like Fermi suggested it was chargeless and massless. By the early 1970s, scientists had shown that neutrinos existed as 3 different types or flavors. These were called electron, muon, and tau neutrinos, and they found a firm place in the standard model of particle physics. What did it imply? That would take a few more decades of experiments, including one of the longest running experiments in the history of particle physics. From 1970 to 1994, experimentalist Raymond Davis measured the number of neutrinos coming from the Sun. But each time, his experiment only detected 1/3 the predicted number. If both mathematical prediction and experiment were correct, where were the missing 2/3 neutrinos? Then, in 1998, Japan's Super Kamiokande Observatory made a stunning discovery. Neutrinos were not zero mass. The experiment also confirmed that neutrinos undergo a phenomenon called flavor oscillations. This meant that even if a neutrino is born as an electron neutrino, by the time it's measured by scientists, it could, quite unpredictably, change into a muon or tau neutrino. Flavor oscillation and the discovery of neutrino mass also shows us why Raymond Davis's experiment showed just 1/3 the expected number of solar neutrinos.
Neutrino physics has thrown up 2 surprises. One is that you cannot tell the mass of any of these particles. I mean, that is the first most amazing thing. Okay, the reason this happens is because these neutrinos, even though they are produced in these interactions, for example, I said electron type neutrino is produced in the fusion process in the Sun. But the moment it is produced and as it starts moving and propagating and reaching the Earth, it doesn't look like an electron neutrino anymore. Instead, it is a mixture of 3 other neutrinos which, with great originality, physicists called nu1, nu2 and nu3. Okay? So, instead of saying nu e, nu mu or nu tau, you have equivalently mixtures of them which are called nu1, nu2 and nu3. Nu1, nu2, nu3 have specific masses.
The 1998 discovery showed just how unpredictable neutrinos can be. As they travel, they change types and therefore masses. Depending on how nu1, nu2 and nu3 mix, neutrinos appear as electron, muon or tau neutrinos, each with different masses. But this staggering new knowledge threw up new questions. What are these 3 masses? Which one is heavier? Which one lighter? And if the neutrino is no longer considered massless, how does it fit into the standard model of particle physics?
You have to now find a new model which will incorporate all these new features or properties of the neutrinos. Then intuition doesn't help you because there is no intuition about something new. Then you can ask this question, so what will happen, so you have some models which use certain symmetry principles which will say M2 is heavier than M3. Some other models will tell you no, M3 is heavier than M2. And ultimately it turns out that unless you do the experiment, you're never going to settle this.
That's where the INOS iCal detector comes in. The iron calorimeter or iCal is a record-breaking detector. When completed, it will be a stack of magnetized iron 50 meters in length, 15 meters in width and 15 meters in height, rising as high as a 5-story building underground. This neutrino detector isn't just a first for India. It will also host the largest magnet in the world at 50 kilotons and 1.3 Tesla.
This would be the biggest magnet in the world. There's a challenge in making the coils, and we just haven't built such things. So this is a big challenge. But I think there's a challenge that the engineers know how to deal with, and it will be challenging, but they can do it.
at Kolkata's Variable Energy Cyclotron Center, or VECC, one can get a sneak preview of the future.
This particular setup is the first prototype of the iron calorimeter, which is going to be built in Theni. We would like to test, like in the main detector, that when cosmic muons they come, so they should pass through a magnetic field. When they pass through a magnetic field which you have created in this middle, they should pass through the detectors which will be installed in the main iCal. So, the main aim in nutshell is to have a small prototype of the main detector and magnet, so that we know how to control the magnet, how the magnetic field look like, how the detectors work for days together under this condition. These layers, like 143 layers you will have. So, the total weight, that is mainly of magnet, mainly of iron, is 51 kiloton. So, in that sense you think about now that 51 kiloton of iron has to be magnetized fully.
Other neutrino detectors around the world use materials like water or heavy water for detection. Then why does the iCal require so much iron? Iron is 8 times denser than water. This means it provides more particles as obstacles in the path of the weakly interacting neutrino.
What you need for neutrino detector is a huge mass, 50 kiloton, 100 kiloton mass, and if you put them and then when neutrinos goes through them, some of them may interact. So, that is why the neutrino detectors are always very large.
And why are we building such a massive detector? Because it will not interact unless you put a really huge detector in its way, so that it can interact with at least some of the time. At the end of this massive detector, per day we expect to see 3 neutrino events.
By now, it's obvious. The particle may be minuscule, but its detection requires mammoth instruments. Even so, scientists only expect 3 neutrino detections per day once the INO is commissioned. Needless to say, if neutrino events are that rare, the detectors had better be extremely sensitive. Particle detectors called resistive plate chambers, or RPCs, have taken years to perfect at both VECC and TIFR.
What is happening here? We are developing these RPCs for the INO laboratory. However, we are developing it from scratch. So, we are trying to understand their performances and then optimizing their design so that nothing will fail there.
These fail-safe RPCs are constructed by placing 2 glass plates parallel to each other. A small gas-filled gap separates the two. The outer surfaces of the glass plates are coated with a conductive coating, and a high electric field is applied across the electrodes. When a charged particle, like a muon, passes through the electric field, it creates more charged particles in the gas. This results in an electron avalanche. In other words, a relatively small electric signal is amplified large enough to be read out through electronic circuits. But RPCs aren't designed only for sensitivity to tiny charged particles. They're also designed for longevity.
The iCal experiment is expected to run something like 15 to 20 years. So, it is very important not only that we want to make these RPCs successfully and characterize them and make sure that it indeed satisfies the criteria that is required for the iCal experiment. We also want to make sure that they run for as long as the iCal experiment wants to run. And iCal requires 30,000 glass resistive plate chambers, the active detectors that the iCal is going to use. And that is indeed a big proposition, because nowhere in the world at the moment there is such a large scale deployment of glass resistive plate chambers.
If you think that the INO's team can rest easy once they've cracked the RPCs, think again. The INO needs a strong network of sophisticated electronics to read out the detector's data.
You may have very good detectors, but without this system they are like blind. We cannot read data from them. Okay, so we need these electronics to get whatever sensitive information we are getting from the RPCs to be recorded and to be analyzed later on. It's basically that if this doesn't work good, then we don't have a good detector.
Every small piece of indigenously developed electronics signifies a giant leap forward in Indian engineering.
We can say that we are going from here to building a new kind of high energy physics electronics that is comparable to anywhere in the world.
As of 2013, many components of the INO's detector, magnet, and electronics have entered an intensive testing phase.
This is our online monitoring system. Actually, as and when the cosmic ray particles are going through our detector, it's getting detected and immediately it gets displayed here. And not only that, of course, these are cosmic ray muons. We will be using these muons also to study certain physics. So while this is the purpose of this setup is mainly for R&D, but at the end of it, we will also get some physics out of it.
What are the immediate physics goals of the iCal experiment of the INO? It's to investigate neutrino flavors and their oscillations in order to learn more about their masses. This is especially critical in light of the recent detection of the famed God particle or the Higgs boson. So far, the Higgs boson has been the linchpin in the standard model of particle physics that gives all other fundamental particles their mass. All particles, that is, except the neutrino.
Higgs cannot give mass to the neutrinos. So, since experimentalists now have discovered the neutrinos have got mass, you see we are now able to take fundamental physics many steps above even the Higgs boson, because it will tell us what is the window beyond Higgs boson.
The neutrino's mass could also open up a different kind of window, one that shows us the future of the universe.
They change the mass balance of the universe, they change the density of the universe. Okay? So they will change also the way the universe evolves, because we know our universe is accelerating, and whether our universe expands forever into what is called a cold death or recontracts back into a second Big Bang will depend on the current density and what is the critical density at which whether it will keep radiating outwards or whether it will close back on itself. Now by adding massive neutrinos, you are changing the whole dynamics and our understanding of how our universe will evolve in the future.
With the INO, India can take a front row seat in global high energy physics, and not just scientifically.
So, INO has this twin project, twin aim, namely not only to discover more things about neutrinos, but also to enthuse students, so that we will create an army of young scientists who will be trained to do fundamental research at the cutting edge.
It's not only just the neutrino physicists that will be participating. You need a well qualified engineers who can build your magnet. You need electronic specialists who can build your chips, data acquisition system, the software gurus who can design the software for monitoring, etc. So all these different kinds of people have to put together. This is a collaborative nature. We have probably, this is the first time such a large collaborative effort is taking place.
It turns out this collaboration is already inspiring a new spirit within the Indian science community.
We find it difficult to collaborate with other people. Of course, we do that with in foreign labs, but doing it among ourselves is going to be a challenge. But I think it's a challenge that we will learn from. We will overcome it, and we will learn how to cooperate with each other, and that will, hopefully this will set an example for other collaborations, big collaborations in India.
A big part of this collaboration is community itself. Local residents around the INO site in Theni are given all the information to dispel baseless fears and misconceptions.
General outreach happened with the public and with concerned environmental activists. Talk to the villagers, just telling them about what will be the impact of the project on them, and also some science. So we have always highlighted the fact that the primary gain from having INO in their site is that they are going to have an educational institution near them. And we have talked to the students in the locality, talking about what kind of opportunities they can have to do research with us. We welcome groups to actually associate with us. For example, American College in Madurai is one of our collaborating members.
Periodically, we go there, we have science, mela and things like that. Whenever there is an opportunity, our scientists go and explain to them what we are doing, and that has created a very positive, atmosphere among the local people now about this project.
When completed, the INO will become a hub for particle physicists from all corners of the globe, drawn to the secrets of the odd neutrino. What stories will it tell us? How will it change the way we view our universe? What will it tell us about our past and future? Curious about the answers? Watch this space. If you'd like to share your feedback on today's program, please send your suggestions and comments to Vigyan Prasar, C24 Qutub Institutional Area, New Delhi 110016, or you can mail us at info@vigyanprasar.gov.in.